Hi everybody. Today we are going to be talking about shell scripting, and specifically in the bash shell. So a shell script is a collection of commands that are all listed inside a file. And all of the commands that we would normally use at the command line can be placed into this file, into a script, and then we can execute the script. And what that does is it causes the shell to execute each line in the script, line by line by line, as if we were typing it in line by line by line. It's a very handy way to take a whole bunch of commands that might otherwise be really complicated to remember and to pre-bake them into a file for later execution. So from a high-level perspective, we have a programming language that has all of the same traditional approaches, the same traditional features as a full-on language like C or Java or something like that. So we see all kinds of the same functionality involved. We also have all the conditionals and loops, so fors, ifs, variables, that kind of stuff. It's interpreted, so there is no compiling of the shell script. There's no variable declaration of it, which looks really spooky. We'll show what that looks like. There's no memory management, so you can't malloc a bunch of memory, for example. You can do a lot with just a little bit of code, and that goes because we are using these Unix utilities in our shell script, and really any program that you choose to put into the script can be involved. All those different tools that are inside it can all be used, which means that we tend to have more full-featured programs available in our shell script. And since they are, it is a standard Unix process that's running, it has access to standard in, standard out, and standard error, so we can grab input from standard in and then write it back out through standard out or standard error. And being a string and file-oriented system is very easy for us to understand. So when do we use these things? Well, often there's going to be something that you want to automate. So maybe you've got a particular script that needs to run, say, every day. Maybe it needs to connect to another website, download a bunch of XML files and store them somewhere, and run a routine to upload them to a database, something like that. Maybe you want to simplify a bunch of really complicated commands into something with just a single line or a single name that you write. So for these small programs, they're great for things that you need to change quickly, that you need to create quickly, that they're very portable, so we don't have to recompile them everywhere we go. A bash script is a bash script. And we want others to be able to understand and open them and read them pretty readily. So often you'll see them used as glue to connect together other programs as well, programs that weren't designed with interoperability in mind. So let's look at kind of a basic shell script here. This is the Hello World shell script. So the first line in a bash shell script, or really in any script that we're running in a Unix environment, we indicate the path to the shell or the path to the interpreter for this script. At the first part, we have the pound sign, which is designating normally a comment, but in this case, the pound sign exclamation mark is called the sharp bang or the shebang, and that is indicating that this is in fact the first interpreter line. So here this is saying for this script, it's going to run this in the bash shell, which is located in /bin/bash. Here we've got a comment line, and here is our echo statement. We're familiar with echo, we've seen it before. Here's echo hello world. That's going to be the first line that's executed. We can create variables in these scripts, and it is as simple as using them. So I start a variable, say myInt, and set it equal to 1, and boom, I've got a variable that is now storing 1. I can then create a variable called myString, or myStr, and set it equal to some text string. Note that I don't even need quotes around that if I don't want it. And then I can take that same myString variable and set it equal to a number, because there's very weak typing happening here. Telling whether a variable contains text or strings, it's not really relevant to what's happening. The variables are just assumed to be of any data type, and it's your usage of them that defines the type inside that variables. We can get the value back out of these things, and to do that we can't just refer to the variable. We use this sigil in front, this extra character that we put out in front, and this is the $sign, and that allows us to get the value back out. So if I say myInt and I set it equal to 1, then I can echo that back out, $myInt, and that actually gives me the value. Okay, now that we can define our string variables, we have the need to store a multi-word string in a variable. And in order to do that, we need to surround the entire thing with quote marks. So the quote marks are going to do two things for us. First of all, they will allow us to control the expansion of variables within the string, and they'll allow us to group that text into a single argument. So here, we're going to use the new printf command. And printf behaves like the C version of printf does, in that it takes a single argument worth of text, unlike echo, which can take multiple words all as separate arguments and output them all. Printf wants only one particular argument to be its string to operate on. So when you pass this into printf, printf is going to ignore the fact that you've got a variable in here. Even though we just talked about it on the previous slide, it's going to ignore it here because we've used single quotes. Now note that the new line at the end is going to be evaluated. So it's always going to get evaluated as a character. If you want to prevent that, you actually have to use 3 backslashes and then the n in order to prevent printf from doing it. Kind of complicated, but that's how you'd actually prevent that from evaluating. From the double quotes perspective, what it does is it allows the variables to be expanded. So if I have a bunch of text in a string encapsulated by double quotes, not only is that represented as a single argument, but also any $ variables that are inside it get expanded. So here, ABTU is expanded into R belong to us, a string text that must have been assigned to ABTU previously. So we can see how those quoted strings are interpreted as one argument, which is critical for printf. So the backslash character, when we're using it not attached to an n, but when we're using it against some other special character like a $, means to evaluate it literally and not to interpret that as a control character. So if I set up a variable nt and set it equal to the string not a chance, then when I use two printfs in succession here, I'll printf $nt. And what that's going to do is cause printf to ignore the fact that that is a $. Even though I've used double quotes here, it's going to tell printf to ignore it. So, and after that, and note that there's no new line character right here, so it's not going to start a new line. Then I'll printf normal $nt with a new line. So that gives us, here's that $nt that did not get expanded, and then not a chance because we did expand it, and then a new line character at the end. Okay, so doing these kind of long commands, so for example at the top here is my long complicated echo -e command that sorts a bunch of text. That is fairly complicated to do. You're not going to want to type that all that often just to get the same result. The reason we use shell scripts again is to be able to do this in one short thing. So maybe CAD and output my commands all embedded inside a script. So how do we build up this script? Well, let's do something silly for a second. Let's imagine that we want to actually build up this shell script from the command line. So if we're going to build up a file, well, in order to do that, we need to be able to echo out the lines that would be part of that script. So let's try to echo out the first line. Here's our shebang /bin/bash. When I try this, I get a really funny error. Bash tells me that the exclamation mark event couldn't be found. The exclamation mark /bin/bash event could not be found. And that's because the exclamation mark is actually part of the bash history feature that lets you go back and see previous commands you've done. So we can't use the exclamation mark directly in that line. Okay, so now that we know what happened, let's try replacing that exclamation mark with the hexadecimal code. So this is \x21. When I run this, it outputs \x21. So we don't actually see an exclamation mark there either. And that's because we don't have the -e argument, which we've seen before. So that hexadecimal ASCII code won't get replaced. All right, so we'll add in the -e, and now this particular line will output correctly with an exclamation mark. I can output this to our file. Here's the create the file and replace all the contents with everything that's about to be sent in. Then here I'm building up all of the different commands. Here's the echo cat, Yeah, here's that new line embedded next to an echo. And every time I want to do quotes inside my script, I have to escape out the quotes so that they'll be stored inside it. This is a complicated, long, nasty thing with finally a sort and an append into the file. Give it execute permissions. We'll talk more about this in a bit later. And then run it. Okay, sure, we could do that. We could try to echo everything out and append it into a file to build up our script, but for the most part, we're just going to use a word editor instead. So we'll use Emacs or VI or Pico or something like that. VI, we actually have a whole lecture coming up on VI. It's my favorite editor for the Unix world. And you can write these Unix files on other operating systems, just as an aside here, but there are differences in line endings. So the new line character on Unix is different than what is done in a Windows machine to designate a new line. On Windows, it uses two separate characters, a carriage return and a line feed, which means the character return returns back to the left and the line feed moves everything up. On a Unix machine, that is simply done as a single character, a single new line character. So if you write these kind of scripts on a Windows machine and then save them on Windows and copy it over to Unix, it won't be able to interpret the new line characters correctly, which is kind of irritating. You can fix that with this DOS to Unix command. You just say DOS to Unix, my file, and it'll fix all those Windows line endings. Okay, so as we write scripts and use variable names, there are some keywords that we're not allowed to use. Those would be things that are built into the shell. So, things like the if statement, and we'll talk about if statements here in a bit. The for, you can't do a for loop. You can't call a variable for because that would overload some of the built-in keywords. Obviously you can't use these things. So there is a way to dump them all out to the screen to view them here, and it's with this comp gen program. And really here I'm just showing off. This is just showing that you can use the -k switch to show me all the reserved keywords at once. But the upshot is that there are some things that you can't use as variable names. Okay, environment variables. Your process, when it runs, your shell script is embedded inside its own new process. It's not just your current shell process running the script. It actually creates a brand new process with bash running your script all by itself, and that has what's called an environment, which is a collection of variables that are going to be available for that shell. And those environment variables control options that could change how that shell functions. So here's some of the common ones. There is a variable called path, and it contains a colon delineated set of directories that bash is going to use every time you run a command. We'll show an example of that here in a sec. There's another one in there called home, which is a shortcut back to your home directory. It also has shell, which is the full path to where your shell is, host name, the name of the computer you're using. There's a ton more of these things. You can get the total list with printf, print for environment variables. That works great for getting the complete list. So feel free to take a look at that. Here is the path variable. Echo $path. It's a variable, a bash variable, which means if I want to get its contents, I have to use the $sign in front, right? So when I do that, I get treated to the list of all of the directories that are going to be searched through. So whenever you're at the command prompt and you type in a command and hit enter, it's going to go through sequentially from beginning to end, looking in each one of these directories for the command you just typed. So the first place it's going to look in is /bin. If it's not there, it's going to move to /sbin. Note that our entries here are separated by colons, which is kind of a weird operator. I'm not sure why that's the one they use but that's what is being used for path. So here's the next one after that is user local bin, and eventually we get up to one in my home directory. Here is my home directory /bin, and then finally the dot. And the dot says current directory. So if you couldn't find that program that we just tried to invoke anywhere else, then look in the current directory and see if it's there. That makes it so that when I run a program in my current directory, I don't have to specify /my program. I can just write my program and it runs. So if I want to look at the home variable, remember that you have to put that $sign out in front. If you don't, it just interprets it as a string and shows you what's there. here is what home looks like for me, and if I echo what the tilde expansion is, the tilde gets expanded in my home directory, and that shows me the same thing. So the tilde variable here, if I try to say, okay, if this is a variable, shouldn't I use a $sign? And the answer to that is no, because the tilde is not a variable. If it was a variable, then it wouldn't have output its text when I didn't use a $sign before. And when I use a $sign, it instead just outputs it as text because there is no variable called tilde. So it's not. This is a feature called tilde expansion, where that thing is replaced with my home directory before it's ever evaluated by bash. And this is pretty much the only place where you see tilde expansion. Okay, so there are a set of special parameters that are available for every script that runs. And these are the common ones. So the process ID of the script itself is stored in the $sign variable. Every running process gets its own unique process ID. So for all the processes that are running on the computer, so that is all the set of programs that have been invoked as running processes that are all running on that system, they all have a unique process ID. Once those processes terminate, those process IDs can be reused, but you're guaranteed that the set of running processes has no overlap in terms of process IDs. Anyway, very confusingly, the name of this variable is $sign. So if you want to get the value of this variable out, you have to write $sign to get it out. So this is going to trip you up, but we'll take a look at that in some examples. Here we have the question mark. The question mark variable, or the parameter, holds the return value of the previously terminated command or script. It's basically a way to say, how did the last command I just ran end up? I mean, what was the value that was in that question mark? Was it a 0? Was it a 1? Did it crash? Did it succeed? That's how we can look at that. And we'll do some examples coming up. The $sign is the number of arguments that were given when the script was executed. The first argument, as of when the script was ran, is stored in a variable called 1. The second argument is in 2, and so on. So 3 and 4 and all the way up. I think there's eventually some limit, but it's a fairly large limit. So one thing to know about those numbers there is that they are variables. So it can look a little confusing for us to refer to them as $1, but that really is the name of the variable and how we extract the contents of it. All right, so there is a little article called Built-in Shell Parameters that will talk even more about this. All right, so let's look at some more at return values. There's a command in bash called exit, and what that does is it terminates the shell script wherever it is in the shell script. So maybe you've got it in the middle somewhere next to an if statement, so that if something bad happens, you can exit your script. So the exit command takes an integer, and the integer that it takes as its first argument is the value that will be reported in the question mark variable. This is the same place for the exit function in C, where it returns a value. These variables are stored in the same question mark parameter. So a 0 is traditionally interpreted to mean that there are no errors in the return result of the previous command. So that we'd call that normal execution. Anything else would be a result with some specific meaning, usually an error of some kind. So if I cat out a program here called exit test, this is a little script that I've written, and exit test has the first line, which tells us that it's a bash script, and then it runs ls just by itself, and then it runs a printf command, and it's going to say where the result of ls is, and then here we $sign question mark new line, and then exit 5. So when this thing runs, exit test is going to run, and it just follows the results of the script. So the first thing it does is it runs an ls. So here's the results of ls. Here's exit test, test loop, and program 1, say. Then it says result of ls is this following, is whatever is stored inside the question mark variable. And that tells me that the result of ls was 0, meaning success. The ls command had no issues, so I can query the question mark variable and see that it in fact had no issues. Once this whole thing terminates, then, after the exit script terminates, it would normally have a value of 0, except I terminate the script with the exit command of a value of 5 at the end of it. So when exit test is finished, it stuffs 5 into the special parameter, and I can fetch that back out after the fact by looking at echo $?5. So in this case, if a couple more examples here. So here's echo hello world, and I see that I get a hello world text out of it. I can evaluate the question mark parameter to see that its value is 0, which means that the echo command succeeded successfully. It succeeded successfully? Yes, it did. It succeeded successfully. Then if I cd some bogus directory and I get a result out of cd that says, whoa, there's no such file or directory, what are you trying to pull? Then I can check out the question mark parameter, and sure enough, there I get a 1 there. 1 says that was an error. Whatever you just tried to do did not work. This whole thing is how the if statement works in Bash. So if I have this is the way if looks in Bash. I have if and then a command list, then and then a command list. Elif is how we do an else if. So elif command list, then command list, else command list, and then I might have, say, like an fi. So this is how it terminates the whole thing, fi. So the inverse of if is fi. So the way it works is that if the command list returns 0, so this is going to be a sequence of commands, and if the whole thing returns 0, then only then will the then clause succeed. If it was not 0, so if this was non-zero, then it'll go to elif, and it'll test this one. And if this one returns 0, then it'll run this command list here. But if that one also wasn't 0, then it'll run another elif statement until it finally gets to an else, which is, all right, none of these are going to return 0, so I'm just going to run this instead. This whole thing relies on querying the value of that question mark parameter. In terms of error handling, Bash does it in a weird way. So if you have horrible errors inside your shell script that are breaking things and deleting files and causing all kinds of problems, the shell script won't stop. It'll just keep running. It'll happily just keep deleting files and destroying things and copying things to the wrong directory because you wrote the script wrong without ever terminating. If you actually want the shell to exit, if any of the commands have a problem, i.e. they're returning a non-zero value, with some exceptions like the if statements, then you would add the -e switch to the /bin/bash inside the shell script. Incidentally, also, most signals will kill the script immediately also. So, for example, if you may be familiar with this, but if you hit Control-C on your keyboard while a script is running, or it's paused, or it's waiting a long time, and that tends to kill the script and return control back to the prompt, what's really happening there is that a sigint signal is being sent to your script, which kills it and returns it to the prompt. We're going to talk a lot more about signals in block 3. So another way we can look at the error handling here, or an example of the way Bash is doing its error handling, is imagine I've got some script called havoc, and in this one I have a normal looking Bash shebang line, and then I cd to some bogus directory, and then I try to run some bogus command and run some other bogus command. So here I give it permissions to run as an executable and then run it. And it tells me over and over again, this command failed, and then this command, and then every command just fails over and over again. But note that the script doesn't stop. It just keeps going. It'll happily keep running with problem after problem. So we can use what we know about these return values to guide the scripts that we write. We can create branching logic inside our shell scripts. So if I have a Bash script that has a copy, and here I'm copying my thesis that I've spent the last 3 years writing, and I'm copying it from here over to some new location. And then in the very next line, I forcefully remove, without asking for confirmation, that thesis. What's wrong with the script here? And what's wrong, of course, is that if the copy command fails, then the remove command is going to blow away our thesis. I don't know why it would fail. Maybe the process gets interrupted or something, or maybe the script gets terminated just as it starts, or maybe who knows? Maybe you're out of space on that drive and the copy fails, and then the remove destroys your file. Something horrible like that could happen. It's not a safe way to go about it. We need to add some error checking here. So by adding -e, as we talked about before, this is going to stop the script if the copy command returns non-zero. So the remove command will only be executed if the result of the previous one was 0. So this is a good way to fix that problem. Another way, this one is going to use the if statements that we've talked about. So I'm going to say if, and then I have a command. And this command is copy thesis to top of my old thesis location to my new thesis location. And if that returns 0, meaning it succeeded, then go ahead and remove. If it returned non-zero, so if this up here returns non-zero, then we get this else command, and it'll say echo copy failed, and then exit the whole thing with a value of 1. So this little 1 greater than ampersand 2, what does this thing do here? Well, what this is going to do is it's a special bash command that takes anything going to the file descriptor 1, which is standard out, and redirects it to the file descriptor 2, which is standard error, for the duration of this command. So we'll talk more about this one later, but the effect of it is that things that were going to standard out now are going to go to standard error. That way, this entire statement goes to standard error. You might be asking, what's standard error? Why do we care about it? Well, what it is it's a separate output location for text to be written to, because when you invoke this script originally, you can specify that standard out goes to one place and standard error goes to another. We have some articles online that talk about this very thing. Okay, so protecting your thesis. Another fix, this one involves the test command built into bash. So we can use the test command to test for things like file existence, equality of strings, the length of something, even permissions, whether a file can be read, numeric equality. So here, this is an integer not equal option. So test, and I'm going to test the value 1. I'm going to do it with an integer not equal to 2. So this is saying that as long as 1 is not equal to 2, then return successfully. I query the result of that, and the result is 0, meaning that is a true statement. 1 is not equal to 2. If I run it with 1 not equal to 1, it tells me that's false, because 1 is, of course, equal to 1. It's not equal to 1. So in this case, I'm going to use test in the same kind of if statement we had before. So I'll run the copy command just by itself. And here it's been removed from the if statement. So it's just above it. So run copy. Then test the value of the question mark that just happened. See if it's not equal to 0. And if it is not equal to 0, then we are going to trigger this copy failed echo command. We'll exit out. But if it succeeded, if this whole thing up here returned 0, then go ahead and remove the thesis. So we really want the value of our parameter here to be 0 in order for us to continue here. Okay, let's look at the bash for loop. So the for loop has kind of a funny layout here, a funny syntax. So we're used to in C, for example, that there are multiple parameters that go into a for loop. We designate the input value, a test that it's going to be evaluated on, and then finally how we increment it each time. All of that is kind of built into the bash loop. So what this is saying is that in this script called for loop, which I'm going to output, we see the shebang line, and then for I, and I is going to be the variable that is incrementing in our for loop. And then we have this keyword in, and what's going to happen here is that this I variable is going to sequentially hold the following values. It's going to hold A, and then B, and then C, and then D. So our test is basically do this 4 times, incrementing the text value each time. And in each instance of this loop, here is the do command that starts the loop. We're going to print out, and I'm going to put some little brackets around it just to make it look pretty. Here's the %s for printf, and it's going to feed in the value of the I variable back into my printf statement. Run this thing through all 4 instances of A, B, C, and D, and then print out a new line. Because remember, this printf statement right here isn't printing out any new lines, which is pretty ugly looking. Run for loop, and here's my A, B, C, D, everything looks good. New line right here, so that my next prompt appears on its own line. If you didn't have this, the prompt would appear here, which is pretty confusing. Now the while loop is maybe a little easier to understand. It's very similar to the if statements that we were looking at before. Here's a program called while loop. So first I'll cat it out to see what the contents of it are. And after our shebang line, I set a I variable to 0. And then I'm going to test that I variable as long as it's not equal to 2. So it starts at 0, and as long as it's not equal to 2, then I'm going to keep running the contents of this loop, anything that's surrounded between a do and a done. So the first line of my do loop is, or inside my while loop, is my printf. I is equal to $i. So it's basically going to tell the user, here's what I currently is, and I haven't stopped yet. And then this line is how we increment I upwards numerically. And we're going to talk more about what this is in a second, but this is going to increment it each time through this loop. So this loop keeps running, each time adding 1 onto I until this I variable becomes equal to 2. And now, is 2 not equal to 2? No, they are in fact equal, so this whole thing returns non-zero, so the while loop fails, drops out, and then we get the printf line stopping I is equal to whatever it is, new line. So the results, of course, are I goes from 0 to 1 to 2 when we see the final stop. Now, one interesting thing is that you can surround, instead of using the keyword test, you can actually use a square bracket. So the square bracket is actually a whole separate program, and often online you'll see examples written like this. So instead of test, you'll see square bracket instead. In fact, sometimes square bracket is simply an alias of test itself. So here's square bracket, and then $e not equal to 2, and we do require this ending square bracket here, just so that we don't have weird syntactical encapsulating characters out hanging by themselves. Okay, so subshells. What we were talking about before is that some of these operators, like the assignment operator and other commands, are going to require strings or numbers to operate on. You can't give them commands. You have to give them strings. You have to give them data to work with. So here's my sample program, and this one is called sumTest. So in sumTest, I have my shebang line, and then I'm setting my first number equal to 9, my second number equal to 3 plus num1. And this doesn't work. When I try to run this thing, even though I've got an echo statement after the fact, when I run this thing, then I get an error that says sumTest on line 3, 1, 2, 3, the plus is saying command not found. So it essentially tried to take 3 and store it in here, but that didn't work because it tried to evaluate plus as a whole separate command. It didn't do this evaluation and then store it in, which is what we thought it would do. So this is why we need subshells. So if we want to increment or set some arbitrary value, we have to calculate that value first, and then return it as text to the script or to the rest of the command that's running, and then that script can continue. So these get executed actually as entirely separate shells, i.e., the script actually executes a whole new bash shell, a whole new process, just to run the dinky little command inside the parentheses or that you're going to run, and that's called a subshell. So it's like these, this is the example I had, these ocean vessels, maybe an oil platform, and they drop some sort of buoy or an anchor or a diving bell. You have to run the operation down in there first, and then once it's done, it'll return back up to the surface. So in the example we had before, where we're trying to increment things, we can do it in one of two ways. The old form way, the old school way, is with backticks. This is the original method for doing this thing. And the backticks say, evaluate what's inside here and return it as text. And when that's done, continue on, and that will then get stuffed into I. So the expression here is a command that is going to do math for us. So expression is a math command, so it'll add two things together. Addition is not a command that you can just do on a line in the shell. You have to have some other program do the math for you. So in this case, it's expression, expr, that fits the bill. The new way to do this is the POSIX compliant method, which is $, parenthesis, and then close parenthesis. Now I like and I dislike this. I like it in the sense that you no longer have to escape things when they're nested. And that happens in the old school way with the backticks, because the backticks have to be escaped with a backslash as you embed them inside other backticks. But every level that you go requires double the number of backticks. So you get this massively complicated line that looks like it's all backslashes in order to get it to run. And you don't have to do that in the new method. You can just put this subshell, this POSIX subshell with $ parenthesis inside and nested over and over again, and you don't have to do any funny escaping. But I don't like it because I don't like the overload of the $ operator. So far in this lecture, we've had 3 separate uses of the $ character. We see it here as the sigil that's saying, this is a variable, get the value out. And now we're seeing it as a character that is establishing a subshell. And we've also seen it as the name of a variable, which is always there, which holds the process ID. And that kind of infuriates me, that this is really the best they could do, is overload the $ 3 ways. So both of these things are going to evaluate that expression and get the results and stuff them back upward, up to the next level. Now, incidentally, there are some operators that can do some fanciness without needing the expression command. So there's the double parenthesis with the $ operator, which can do math directly. We can even skip the subshell component if we just want to do math directly and just increment I by itself. We don't have to use the expression command at all. We don't even have to use $signs. So double parenthesis is just do math and run on a single line there. So that's pretty handy. Okay, so let's talk about trapping signals for a sec. This is needed in program 1. Now signals, we're gonna touch them just really quick and then back off, because again that's a block 3 concept. But signals is information that's being, it's a type of information that's being given to your process to tell it to do something based on the type of signal that it is. It's like red light, green light, that kind of thing. And SIGINT is the classic one generated by Control-C, and it means interrupt. So we can use the trap command to catch this signal and do something. So the usage of this thing is that we would establish the trap line, or we'd put the trap line in our script, and then the next argument is the code that we're going to run. And the third argument, and all the way up, third, fourth, fifth, however many, is the list of the signals that will trigger the code to execute. So in our example down below, we can see that we've got our shebang line at the top, and then I set a variable called TMP. This temp variable contains a name of a file that I'm going to be using. But as of this moment, it is only a string. It's not a file. It's not a file name. It's just a string. And that string is my cool file name, and then this $ here is the process ID variable. I have to use the $ to get the value of it, which get this funny, confusing double $ construct. But really, what that thing is the process ID. Now, by putting this at the end of this string here, I'm getting what should be a unique string that I can use to create as a file, because it's essentially a way to create a temp file with a unique name, because I'm the only script that's running that has this particular process ID, so I should be able to create temporary files and use them such that they can't be overwritten by other processes because they're not using the same process ID. So if all of the processes followed that same logic, then they'd never overlap. Alright, so there's our string. And our next line is our trap command. So the first argument is all of the command that's going to run, and it's everything surrounded here by double quotes. So what's inside here is a remove -f of the temp file. So remember that -f says don't ask, so just blow it away. I don't care if it's there, if it's not there, just go ahead and run. In fact, if it's not there, it won't even complain. It'll just return nothing. Then the remove command is looking for a file with that name. So $temp means get the value stored up in here as a string, and then the remove command is going to look for that as a file to delete. Then echo that we've received a Control-C and that we're exiting, and then exit with the value of 1. So this is us catching the following signals: int, so interrupt, hang up, and terminate. and then use, so receive that, and then blow away our temp file, indicate to the user what happened, and then exit out. This is better than leaving our temp file behind. We don't want to leave the temp file behind. We want our script to clean up after itself. So in order to do that, we catch the signal that was going to terminate us, clean it up, and then exit. So after that trap statement, I have some echo commands. So here's a whole lot of text dumping into a file. And then I'm going to run a while loop that is a never-ending loop. So as long as 1 is not equal to 2, then do this forever. And since I'm not changing, since these are number values that can't change, this is going to run forever. And it eventually says hit Control-C to exit. So one important thing about this is that the trap statement needs to be near the top. If the trap statement was underneath this while do done structure, it would never have been run and wouldn't be active. So that when the Control-C came in, yes, it would kill off the script, but since trap had never been run, then it won't do the cleanup routine and it won't output that to the user. So remember, trap statements need to go as close to the top of the script as possible. It can't go on the very top line because here I'm using this temp variable, and since I have to use that essentially by declaring it first before I can use it in my trap line. But yeah, my trap line needs to go as close to the top as possible. Now there is an error in this script. Do you see it? And the error is right here. So what's causing this error? This echo is going to send text, and it's going to create it in a file called TMP. That's not what we intended. What we intended is that this should be $TMP, i.e. get the value of whatever the file name I specified up here was, and create a file with that name and put the file inside there. As I've written it here, this is simply going to take lots of text and dump it into a file called directly TMP. So the value myCoolFileName process ID is not actually used as part of this echo statement. So later, if you try to open up a file with this name, myCoolFileName, it won't exist. And instead, you'll have this file called TMP. So watch out for this classic easy to cause error. I think that is going to do it for us today. If you have any questions, please hit us up on the discussion boards. Happy to answer and take a look there. Thanks, everybody. See you next time.